So now we're going to actually talk about something which is going to be very useful to you. Although the specific steps are going to be very, very much dependent on exactly what you want to do. And so if you can follow along what I'm doing, that's fine, but don't expect this to be something that's exactly relevant, in terms of step by step, because the task today is to build a new experiment. And of course, you're not all going to be building the new experiments for your research. You're going to be building different experiments for your research. So one of the first things which we tell people to do, don't start from scratch, never start from scratch. You always need to find an example, a working example of something that's somewhat related to what you're trying to do. MOM6 examples has quite a few experiments. They've been classified into groups. So we've got various coupled model configurations, ice-ocean coupled model configurations, and in the ocean-only directory, we've got over 2 dozen worth of examples. Now, as examples, they may not be particularly good examples because some of them have been thrown in there as things for us to help test the model. But a lot of them are actually good examples. So Phillips is one example in case, double jar is another example. And those are stacked shallow water models, but there are realistic model examples here. We've got some process study examples. The best thing to do if you're looking for some starting place is come and talk to one of us who knows this repository or know where there are other repositories. There are plenty of other repositories unrelated to MOM6 examples, such as the Ocean Eddy CPT has its own repository of examples, and then there's the regional model, ESMG, organized through Rutgers in Alaska. They have a set of regional configurations, which are good starting points if you want to do a regional model. So come and talk to somebody who's familiar with the model for where a good starting point is. So what we're going to do is just kind of have a thought experiment here. We're going to say your advisor has said, hey, wouldn't it be interesting to look at some two-dimensional turbulence over topography? No one's thought of this before because he's an advisor, so super statement. But this is the sort of thing advisors you have to deal with when you're a student. So stupid advisors. So anyway, so you go off saying, okay, well, I'll make him happy. I'm going to see how to do this with MOM6. And so you knock on Professor Bob's door, and you say, Professor Bob, what's the best starting point if I wanted to study bioclinic turbulence over topography? And he says, well, there was a good paper I wrote in 2013 that used the Phillips model. You could probably adapt that. So that's where we are right now. We've just run the Phillips model, having been told to start there. And now we're going to just go through an exercise of trying to start from that and develop it. So this is going to be a trial and error experiment. This is how we all do it. We do it by trial and error. You change one thing at a time, it doesn't work. You look at why it doesn't work, and then we move on from there. But one of the key steps was to have it working. So again, if you want to do this yourself, hopefully you've got the same MOM overrides already run with 100 days of output, 10 snapshots. You can find that to cut and paste in the MOM6 examples wiki AOS workshop notes. Just for today, they'll be there. And so if you've run that, I was able to run it with 4 cores on my laptop here, and that's what we're going to switch to now. So that ran in about a minute, and I'm going to make, the first thing I'm going to do is kind of make it go faster because we can't be affording to wait for a minute for every time I change this. So one of the key things I said earlier is start from a working example. So the very first thing you have to do is actually take a vanilla example, don't change anything, just to make sure that it actually worked, and look at the output. Now to look at the output, I'm going to use Jupyter, and I'm going to take some shortcuts here. I've already installed a Python environment following the wiki page, but we have, so let me just make sure I've got that active. So conda info -e. So I created an environment called MOM6Py, MOM6 tutorial. If you're using that already from the last session, then that would work just as well. I'm going to activate it. MOM6Py. And now I'm in Phillips 2-layer example. I'm just going to start a Jupyter notebook here. So that I can do stuff, and I'm going to look at that web page. And there is notebook. Right, so now I'm going to create a quick notebook just to do some quick. I need to be able to look at the output so as we evolve in this experiment. So I'm going to do a sanity check. Let's import X-ray. And I'm going to create a data set, open a data set. And we're going to look at that prog file that we've already looked at. I need some quotes on that. And if you see me making stupid typos, please, I'm going to stop times. I'm going to turn off reading times to avoid some errors. That should give me that. That's what the file looks like. And now I'm just going to make a quick plot to see what things look like. RV, I'm going to use the last timestamp. And that's three-dimensional output. I'm going to change it to ZL equal to 0. That's the surface. Now it's two-dimensional. Now I'm going to plot it. And that is the relative vorticity at the end of that 100-day run of Phillips. And we just saw exactly the same thing. I did things a lot quicker because we need to move along. So it hasn't got all of the correct steps for doing the coordinates and everything that Raf just talked about. So what we're going to do now is start evolving experiment. We're confident that the model's running as expected. This looks like one of the plots in the paper. And so we're going to now switch back to where we ran it. I'm going to start modifying the experiment. So now, 1 minute's a long time. The first thing I'm going to do, and this is something that's actually recommended when you're developing an experiment, if you're trying to develop something where you've got lots of turbulence and it's meant to be high resolution, don't develop the high resolution version of it, because it will take you days to run each version of the model, and you won't make any progress because you're waiting so long for the model to complete. So the very first thing we're going to do is we're going to change the resolution of the model. So I'm going to add an override, and the number of points in the model globally is in the parameter ni global. And it's currently set, actually I could show you what it's set to in a moment. I should really do that, shouldn't I? This is, I'll catch you here. For the record, so I've just changed NI global to 40. And if I just look at NI global from the current configuration, you'll see it was 60 and the J value was 80, I believe. So I've just made the model almost smaller than half of quarter of what it just was. And if I run that, it's going to go a lot faster. So I'm just going to verify that by running it. Last time it took over a minute. And now you'll see that it's going to zip by in 100 days. It will be probably half a minute or so. So that was the first thing I'm doing. So the first thing you do is you don't try and develop at the resolution you're targeting. You make the model smaller so you can afford to experiment, okay? Because you're going to do an awful lot of trial and error experimentation as we're about to do. Yep. So if you go to the AOS workshop notes, the second section has the first two lines. NI global is 40, NJ global is 40 with overrides in front of them, and I'm putting this into the MOM override. So this is the final state we're going to be in this override. Don't cut and paste the whole thing because that's cheating. I want to show you some of the mistakes that we make when we're going through this, okay? So the first thing is that this ran faster, so it only took less than half a minute, so on my laptop at least. John? Close the notebook. Okay. So that's good to know. Did you all hear that? That if the file is open in Jupyter, you might not be able to rewrite to the output files. So before you run the model, I know that doesn't happen on the Windows Linux installation, so don't panic. But it sounds like that might be a Mac issue. But anyway, so if you want to close everything in here, what you would do in the notebook is you would just do a restart, and that will just close everything, or restart and clear output, and that will just close everything. That will kill everything that in your notebook, so you could then write to the file again. So all I've done so far is import Xarray. Oh, good idea, good point. How's that? So import Xarray. As I said, I'm doing the analysis part of this in a quick and dirty way. Okay, so we've run the model, we've just changed the size, it ran faster. And so now, having just restarted the notebook, I'm actually going to do what I'm going to do regularly, which is I'm going to restart and run all. I just want to rerun the notebook just to see what happened, okay? So just going to quickly do that. So it's as if I had typed out import Xarray, ds open the prog file, look at the ds, the state, and then plot again. And now what you'll see, if you remember what it looked like beforehand, is actually a lot coarser, coarse-grained, but it's still doing something useful and interesting. So that means I can use this to develop what I want to do. Now, the first thing that you might notice about this is this model is a channel model. We saw in the output that VAF showed us earlier that there were some NANs. If you look carefully, those whites are the wall that's in there. And so what we want to do is you want to look at two-dimensional turbulence and more isotropic. So we're going to actually get rid of the period, we're going to get rid of that wall in the north-south direction. We want to make this doubly periodic. Okay, so that's one of our first tasks. So the parameter that controls that is reentrant. Gosh, what's it called? It's reentrant X and reentrant Y. So if I grep for reentrant from the doc.all file, you'll see that currently reentrant X is set to true, meaning it's periodic in the X direction, but reentrant Y is set to false. So what we're going to do is we're going to set reentrant Y to true, and we're going to do that again by editing the override file. So reentrant, oops, I'm going to put an override in there, even though we don't need it because it's already set to reentrant Y is equal to true. So I'm going to run that, okay? And this is one of the other things is, every time you make even one line change, just rerun it to find out what happens. So we're going to run the model again, 25 seconds later. I did need it because I'm explicitly set to false, so I was mistaken. Now, there are several things that have just happened. The model got to day 29. I'm sorry, what was that? We're at 50 minutes in already. We've got a few more lines to go through, quite a few more lines to go through. Well, what's this? You want to? Yeah. So how are we doing? So I've just changed one parameter and the model has crashed for reasons I'm about to explain. Really? So far I've set reentrant Y as to true. We have just set reentrant Y equal to true. It's right there, bottom of the screen. Okay. Nothing really wrong goes to happen. We need to make that a fatal error. Yes, but we don't by default do it. So, yeah. That's a different conversation. Okay, so we've just made the model doubly periodic, and the model ran for a little bit and then crashed. Okay, so we need to start looking at what's going on. And one of the problems is sometimes you won't actually have any output to look at because the model just crashed and hasn't had time to write. We can actually find out whether that worked or not. I don't know if it will have written anything out. I'm just going to try rerunning this. It's probably not going to let me read the output because we actually got lucky. So you'll see that it hasn't managed to write the output properly. So we're in this kind of bad state. So now we're going to have to start thinking about what's happened. Now, this is the case where you would actually have to do a lot of investigation. And I'm just going to show you the one key step that was going on here. So what I'm going to do is I'm going to do an even dirtier analysis trick. I'm going to open the data set, and I'm going to open that a file called ocean geometry, which the model always writes, even though it's not in the diag table. So this is a MOM6 specific output that we have because it lets us bypass any problems with initialization of the diag table and all that other stuff. So this is an output directly from the model. I'll just show you what that looks like. So that is, it has all of these metric factors in this is kind of the stuff, this is kind of essentially the raw grid information. And I just want to show you that there is a variable f, which is the Coriolis parameter, and I'll just plot it for you in 2D. And you'll see that it's varying. And I just made the model reentrant in the y direction. So now it's doubly periodic, but f is varying with y. And so I have this big discontinuity between the bottom of the model, the south of the model and north of the model. So the first thing, so I just know, after a lot of investigation, and of course you knocked on a few people's doors, say, what's going on? I've only changed one parameter, and you eventually discover, oh, we've got a variation in f, and we really, because it's doubly periodic, we needed a constant f. So that's not what we're going to do next. Is we are going to. So what we're going to do now, having just made the model reentrant, we've discovered that in order that we suspect that we need to set f to get rid of beta. So we're now going to override beta equal to 0. I'm going to show you what that looks like again. So now we've added another line, beta equals 0, hash override beta equal to 0. Okay. There's the override. So we've now got reentrant in the y direction, beta equal to 0. We'll try running the model again. It ran a few time steps. So basically, f was varying from of order f, in fact, over one grid cell. It's like a very strong beta in the wrong direction, yeah. Okay, so this time the model completed. It ran 100 days in under half a minute. And so I'm going to get rid of this. Well, actually, why don't we just do that there? So I'm going to rerun this notebook again, restart run all. One of the reasons you keep on restarting the notebooks is even if you didn't have an error when you were running the model, sometimes Jupyter remembers the handles for the old file, and then you're not actually reading the new data. So it's just good to restart the kernel essentially just to make sure you've got a clean sweep. Okay, so now we've got this going on. So we've got to definitely change the output. You can see the stuff happening in the model. Not quite what we were hoping for, but also f is now uniform. Okay, so I'm going to get rid of the cell now that we've got f as uniform. Yeah. Okay. So getting rid of that cell. This is the output we're interested in. This is the relative vorticity, and you can see that. So actually, now that since we're seeing that, why don't we just look at the beginning of the model? So this is time is 0 is the first entry in the diagnostics. That's not the initial conditions. It's always the first time period in the analysis in the diag table. So I'm just look at that, and you'll see that we've got all this zonal stuff going on. We've got this very strong initial perturbation, which is actually where this is coming from. But also the overall shape of this is not and I don't think I want to have all that stripes going on. And so now we're going to actually say, well, okay, what was this experiment actually set up to do? And the answer is, it was set up as a channel model, and the forcing and initial conditions were all set up for a channel model. Remember the profile, there's the section for the zonal flow with interfaces. That initial condition also had a discontinuity at the north and south boundaries. So now the model's running, but it's not actually the forcing or initial conditions we want. So this is where you might actually end up writing some code because you want to change the initial conditions. I will just quickly show you. Maybe I should go here. I'm going to show you some source code. This is in the source user directory. You don't need to follow this yourselves. I'm just going to show you that the Phillips model, Phillips initialization is the module we're using for this experiment. And you'll see that the initial thickness function happens to have, these are the parameters jet width and jet height that's controlling it, happens to have this profile, and somebody, very luckily, has actually changed that profile when it's got this reentrant y equal flag. So we should actually have zonal initial condition already added. That's actually one aspect. But the jet height and jet width parameters are specific to the original profile, and that's being used differently here. So I'll tell you now, I'm going to shortcut that we actually just need to change the parameters in these expressions because we have repurposed the same parameter. I warned you that the meaning of these parameters changes with the state of the model. So in this case, we've got a tangent profile with a profile which is the jet height and the jet width in a tangent profile, and now we're switching it to a jet height, it's amplitude again, but the jet width is now inside a sine, And if you wanted to be periodic, we did see that it was periodic, but the width of that periodicity, the length of that periodicity, should match the width of my domain if I want to have a nice large-scale forcing, as opposed to the short one, which we had in the tanh profile, okay? So this was all because of a change of formulation of that forcing. We need to change the parameter. So that said, we're now going to modify that parameter. So this time we're going to add an override for, what was it called? It's called jet width. And the model domain happens to be 1600. That's something we could have looked up, but is it that? I've got 2 hash frames, so I'm going to get rid of that. And I'm also going to change the height. We'll do that later. The width is currently in kilometers, yes. Okay, so we're going to run that one more time. Again, make one change, run the model, see if you can make it work. Just jet width. Correct. You can always override, but then you can't secondary override it. Yeah, you are correct. You do not, if for something that hasn't been used, you do not need the override, but it's never wrong to always have override there. But go ahead, Bob. Do you want to grab a microphone?
Well, no, I understand that. But my point is that has to be defined as a runtime parameter or at the runtime, right? I'm making a very bonehead statement. Right?
Do you want me to comment?
I'm trying to slow you down. I'm trying to slow you down.
Okay, so.
Do you want an answer?
No, I'm fine.
Well, so the answer is we are trying to make sure that every dimensional value that you're using is something that you provide as a runtime parameter, even for these user cases. You are free, subject to the rules of Fortran, to hard code a number. But it's pretty easy to add a new parameter for something like the jet width and the jet height. It actually does some useful things. It documents what it was. It does some unit conversions. The internal version of the units here have gone from kilometers to meters, or actually meters times some integer power of 2 and some other things. But increasingly, we would like to encourage everybody, even in user cases, to add your parameters as runtime parameters so that they're getting properly logged. It is not such a bonehead statement as you might think.
Okay, so we just modified the jet width. So this is the current state of MOM override on the screen there. And I'm going to just again always rerun the analysis to see what the model is now doing. So remember, this was the fine scaled. It was periodic, but much shorter scale than we would want for our experiment here. So I'm going to rerun this. And okay, getting somewhere. So what we're seeing here is some turbulence overlaying something. What's going on? So actually that basically, this is the initial conditions. So I've just remembered. So what we're looking at here is time. This is the first time shot. Remember, we've got this large amplitude perturbation. I'm going to just look at the end of the model again, just to see how it evolves. And you'll see that in fact now it's a much more uniform isotropic turbulence going on. Okay, so we've now got eddies which are being forced by a large-scale sine in the y direction. So we're restoring the interface positions to this sine shape, just as in the Phillips model, which used to be a tanh. And you can see that the eddies, the vorticity filaments are spanning both boundaries. So you've got a kind of a filament that is going off the south here and is on the north there, and we've got this filament on going off the right here and it's coming on the left. So this model is now doubly periodic, and if we were to animate this, we would see this stuff kind of evolving and so on. Go ahead, Steve. Question. So this model doesn't have any. Oh, well, I did say that.
But
You didn't talk about the initial condition restoring or the boundary forcing.
You're correct. I didn't explain that the original, thank you. The original configuration that was run for the, the original Phillips model that we started from has this initial condition, which is this interface tangent profile. And in fact, it also has a restoring of is in the Hallberg 2013 paper. There is a term added to the model. It restores the mean of interface height to that profile. So that's the forcing we're using. What we've done is we've just changed that profile in the code by turning on a flag, which happened to be there for us in this case. Added years ago, not for this tutorial. Okay, so we now have the two-dimensional turbulence part of this, but now we've also, but your advisor also asked you to add some topography and look at what's happening there. So this is again, this is something where you would normally want to go and look at some code and modify some code if you needed to do that. There is another experiment in here called C-mount initialization, and that simply adds a Gaussian topography to a model. And so we're just going to actually reuse that module now, because all of these topographies, these user codes are accessible at runtime. So what we're going to do is in the override, we are going to change a parameter. I'm going to put a space above this just so it's a separate, because this is now adding the second level of information. We're going to add topo_config, which is a string which names the topography. So we have quite a few topographies available. I'll show you what the options are in a moment. So we're changing topo_config to C-mount. Now let me just show you some possible topographies. So if I head back up to MOM6 examples, go to ocean only, let's do Phillips, since that's what we're looking at, momparameter.all. And if I search for topo config, there it is. So topo config in the Phillips model was flat, meaning no topography, except for the rearrangement channel adding a wall. But we have all these topographies already coded up. So we've got bowls and spoons, because that's a classic oceanographic feature. We've got some idealized realistic worlds in the sense that they kind of have continents and continental shelves like Benchmark and Neverworld. And there are some process study configurations like Dome and so on. So there's already a choice of topographies that we could have used. And I've just chosen C-mount because it's kind of easy to, rather than writing code on the fly. But you can always add, if you need to, add your own code to define and analytically define topography. Or we could have even used file, which would read the topography from a file. And that's actually how the global models all run, because we don't have an analytic description of global topography. The reason that file is harder work is if you want to keep on changing resolution, which is something you're doing when you're developing your experiment, you have to regenerate all the topography files every time you change the resolution. That's kind of inconvenient. It's something you would have to do if you were file-based. But this is why we kind of find it easier to work with writing things up in Fortran, because you can just make things dynamic. Okay, so we've just added C-mount, and there is actually, I'm just going to run it because I said I will run it every time I make a change. So I'm going to run it to see if it actually works. And I can't actually remember which of these steps do and don't fail, actually. I think they all work from here on. And I'm just going to actually then look at the parameter file, because there's two parameters associated with C-mount, which are its width and extent and height. So I'm just going to see what they look like. Now that we've turned it on, we'll have these parameters. Previously, they weren't available because we hadn't turned on C-mount. So now I'm going to look at the parameters at all short. Well, let's just do all. And you'll see that the C-mount delta has a value of 1/2. This is the non-dimensional height of the C-mount. And then the length scale was set to 20. That's not very good, because we've got a domain of 1600. So we've basically got a really sharp delta function. And we had no length scale in the y direction. So we've added a ridge. Let's actually make it a C-mount. So I'm going to just do that now. How are we doing time? 10 minutes, good. So I'm going to just C-mount x length scale. Some of our parameters are Does it go there? Yeah, it does. And I'm going to make this 200 kilometers, so it's resolvable with our current grid, but not so. Actually, I'll make it a bit larger. Why not? And we need a Y scale. I'm going to make it an actual Gaussian bump rather than a ridge. Okay, let's see what happens. So I'm going to run that again. And again, yeah, sorry. At this point, we are currently. This is the same. This is now pretty much the same line for line for the one on the AOS notes page. Blank lines don't do anything. They're skipped over. Yeah. So we're going to run the model, and now we're going to look at the output again. So let's pull that up. Some of us find it very soothing to watch the model running like this. You know. It means we haven't made a mistake yet. Good. I'm adding them as a matter of safety to avoid accidental ones which I need them as opposed to ones which don't need them. If it's working without it, you don't need it, and so you don't have to have it for those particular parameters. Okay, so we're gonna do.
If you ever needed it, it would be a fatal error.
Correct. So we're going to restart and run this analysis, and now we've got something. Oh, now do you see that there is something larger happening here? This eddy looks a little bit larger. It'd be kind of nice if we could actually do some analysis. This is where you need to actually have RAFs tools already up and running, though you'd actually start looking to see whether that feature is making a systematic effect on your upper layer vorticity. So this was just a kind of walkthrough, one line by line, modifying the experiment towards where you want it. There's many other things we could have done. We could have added surface forcing. We could have changed some of the closures in the model. But each of these steps, you really must just say, take one step at a time, test, look at. Now, there's one last thing I haven't got time to go through this, the next thing which I really want to advocate for. But let's say that you've spent some time developing this experiment and you're very happy with it. The last thing you should do is do it where I've just done it, okay? So we've just done this in Ocean Phillips 2-layer. That was because we wanted to just show you how you go through this process. But in fact, what you should have done is make a new directory that describes your experiment. And this experiment was called the Fred experiment. And in that Fred experiment, we should have copied in the things that we know that we need. So that would, that would be the input name, the input file, the direct table, and the MOM override and MOM input. Oh, sorry, I keep on making mistakes here because I'm flying. So this we know to have been the bare minimum for the model to run, and that hasn't changed yet. And we know that if we wanted to, for the model to run cleanly, we should have been doing it in a new, so that's the first thing, is actually start a new experiment and copy some, start from a working model. But the first thing you do is actually create your own copy of it rather than working there, because after all, after those changes we just made, it's no longer the same Phillips model. It had topography, different forcing, and so on. Okay, so that's. But the next thing is, you should not also do what I just did of just changing, line by line, testing, and evolving continuously without recording it. So we've been writing a file, but we just made about 10 steps. And if the 10th step had not worked because of one of my steps earlier on, like the 5th step, you now have to actually kind of, in your head, keep track of backtracking and all of that stuff. And remember, this process is probably taking you a few days so far. You should not have actually been just changing the files and trying it. What you should have been doing is using a version control system to keep a copy of your steps logged using Git. We're going to learn about Git tomorrow, hopefully. Is that right? Yeah. So it is highly recommended that the very first thing you do is you create a repository and you use Git to version control these input files, these ones here, the 4 input files, sorry, not the output. We really recommend you doing that. And there's actually, in the MOM6 example wiki, gonna have to keep on backtracking up. Oh, it's actually here, yeah. So in the MOM6 examples wiki, there is, under the pages, there is an actual page called Create Your Own Repository of Experiments. And it gives you the steps you need to do to not only make a copy of a directory and start running, having a directory named Freddy, the name of your experiment, but in fact also to keep a record of it on GitHub, which is the right place to do it. Even if you make it a private repository, it doesn't have to be public, but keeping it on GitHub is a sure way of never losing your file. And as we had a conversation at lunchtime, the Scratch file system where we've been working, if you're on Stella or on Gaia, can disappear. And it has done in my career a few times. And luckily, after the first time it happened to me, I learned, don't keep anything of value in a Scratch space, okay? So two real points. Don't evolve Philips itself, make a new experiment directory descriptor to you, but also then start using version control to monitor your progress through this exercise of tracking the evolution of the experiment, because you will need to remember and record what you did. And as you look through those, you'll realize when the 20th step or the 100th step that you make doesn't work is because something earlier, and you can replay it in the right way. So this is again back on the wiki under pages. There is a create your own repository of experiments page. It's under the pages. It's not from the getting started. It's just so this is just a page where we are just outlining general advice for how to actually go through the process of setting up your own repository, because it's good practice for you to just do this always, to keep a log of what you're doing as you're evolving things, okay? So that's all I wanted to show you, kind of step by step. Model can fail, don't panic. There's people to talk to. But this is one of the reasons for having this workshop, is to say you guys should be able to, now you know who we are. If you're trying to do this, we're here to help. And this is something that, if you will, starting from scratch is never the right way to do it. Always start from something that's working and evolve it step by step towards what you want. That's all I was going to say. There's plenty more we could have said, but we have run up against our next time boundary. Okay, so any general questions? Bob, you have a general question?
More of a comment. You added the override and the input file, but you didn't add the parameter doc files when you created Fred. Yeah. Is that a good idea?
No, I totally agree. Recording what the model wrote out, at least in the mom parameter doc all at the very least, but the other ones are actually kind of useful. Evolving those, because those are a record of what the model actually did. And if you have a diff the mom input with the mom parameter dot short, as I showed you earlier, although they weren't perfectly in sync, it gives you, it lets you check to make sure the model actually did what you thought it was going to do. You can always, that's a step you can take advantage of. So keeping a record of that is nice. And also, you'll notice that in my mom override, I wasn't adding any of the auxiliary information like units and so on, because the model doesn't read them. But the model does write it into those files, and so it's telling you which units to be used for the jet width, for example. It was reported in kilometers if we actually looked at the generated output.
Why not just copy everything? Because you're going to overwrite the. Why does it do this? And it's terrible. You're going to overwrite the output files anyway. So why not just copy everything?
Yeah, we could have copied all 8 files. That's what Bob was basically saying. But you don't want to store the netcdf binary file just because they're going to be big. That's the last thing you should be versioning, because you can't do a visual diff of them. Storing binary files and versioning binary files is another conversation. But the text input files and the text output files definitely should be versioned, and you could have copied them all. That's fine. Akash, wait for the mic. Wait for the mic.
Is there any tutorial on creating your own, like a custom grid file, custom initial conditions file?
So there are several packages. I think RAF has one for generating grids. I know that Nikki Zade has a grid generation package, which we can, I think there's a link to it in somewhere in the wiki pages, but we can make sure, this is a good question, we'll make sure it's linked there. But also Rob Cermak has created some tools that were posted in CSM, and I think linked somewhere from our repository. And then the SMG group, also James has been working on some of these tools, I think maybe with Rob. So there are a lot of packages. There's no one way to do these things. So there's always it's actually kind of nice that there are multiple packages for doing these things, because they focus on different aspects of grid generation. Do you want to, is there anything to say or add to that, Enrique? Because Enrique's group has been doing some of this work.
Yeah, so the packages that we have through ESMG or either Rob Cermak or James Simpkins, GitHub pages are more focused on regional grid generation. We have not done global. I think the global is a much more involved and different animal.
So for the global, if you don't include a tripolar cap at the Arctic, some of the options, like Cartesian was the one we're using here, it's easy enough to add a Mercator grid. It's a simple latitude longitude grid, and somewhere there's some equatorial refinement. So those are things that can be internally generated. Once you start getting into tripolar grid, and then around Antarctica, we sometimes like to stretch the pole from the geographic South Pole into the kind of the middle of East Antarctica and some other things. That's where you're really looking at kind of more dedicated packages, writing it to a file, writing the supergrid to the file, writing the topography to the file, and generating your grids that way. But there are lots of different ways to do it, depending on how complicated and the details of your specific way of doing it. There is no one right way to do it. Just
how do you do the landmass?
the way we do the landmass is with the topography. If the topography is shallower than a certain value, that's land. If the topography is deeper than a certain value, then it's not land. And this may be getting a little bit beyond this, but one of the tools that we like to use is something we call ICE9 from the classic science fiction story. You touch one part of the ocean, anything that touches that part of the ocean is also ocean. And it's a way of figuring out if you have disconnected bits of the ocean. So if you try this naively with a topographic data set, you might find that the Black Sea is not connected to the ocean. We would go in by hand and put in the connections between, say, the Black Sea and the Mediterranean and the Atlantic as a way of doing that.
Any other questions? So it is coffee time. So there's a schedule I have in my hand. And this it says 3 o'clock break in the atrium. And then at 3:30, we're supposed to be coming back to hear about how to build your own experiment. So it turns out we just did the wrong order. I should have talked about the parameterizations just now, but we'll be talking about parameterizations when we come back at 3:30.